viewers and students. Here is another video about problems uh, given as civil engineer licensure exams in hydraulics. I hope that through this video, your skills and knowledge in hydraulics will be increased, further enhanced for you to prepare for your licensure exams. So let's have the first problem. A spillway 2 meters deep goes over a dam 40 meters high. If the coefficient of wear, which is 1.705, this is also the coefficient of a broad crested weir. In this case, it's a dam. What is the energy after the jump? And this can be addressed by using the formula for discharge in a rectangular channel that goes a jump, and that is small q square over g equals 1/2 of depth 1, depth 2, quantity depth 1 plus depth 2. From there, we can compute the energy after the jump, which is energy 2, which is velocity head at section 2, v2 square over 2g plus depth 2. Before we can solve that, we also note that the energy after the jump is energy at section 1 minus head loss in the jump. The head loss in the jump when the channel is rectangular is equal to depth 2 minus depth 1 quantity cube divided by quantity 4 times depth 1 depth 2. And you just refer to the derivation in open channels about hydraulic jump when the section is rectangular. Of course, this is a rectangular channel. The spillway or the dam may be treated as rectangular channel. So between the upstream side of the dam and the apron where we have depth 1, section 1, and V1, we ignore losses because it's not stated in the problem. So if this is the dam, this is the height of the dam, 40 meters, and that's the depth over the crest of the dam, which is also the spillway, and that's 42 meters. So that's why this energy at section 1 is also 42 meters unless otherwise specified in the problem. So we can relate depth 1 in terms of V1 and vice versa by first computing the discharge. So the discharge capital Q for rectangular channel is this coefficient here. This is already greater than 1. So just like Francis formula, 1.84 length of the crest times head to the 3 hubs. In this case, 1.705 length of the crest head to the 3 hubs. The length of the crest may be taken 1 meter because there's no mentioned length of the dam. So we consider 1 meter width so that the discharge will also be small q. So E2 is E1 minus head loss in the jump. The head loss in the jump is simply quantity depth 2 minus depth 1 cube over 4 times depth 1 depth 2. So first let's have Q. E1 is 42 and it is V1 squared over 2G plus D1. To relate V1 and D1, we must compute Q first from the wear formulas 1.705 C sub W times length of crest, which is taken 1, times head, which is 2, to the 3 hubs. Solving for Q, it is 4.822 cubic meters per second per meter. Then, since Q is also depth 1 V1, then from there we can express V1 in terms of depth 1. So V1 is 4.822 over depth 1 into this equation. 4.822 over depth 1 quantity square over 2g 19.62 plus depth 1 equals 42. Using your high-tech calculator, we can now compute depth 1 as 0.1683 meter. Then E1, then since head loss in the jump can only be computed if we know depth 2, so to solve that, we use the discharge q square over g, small q square over g. The formula, hydraulic jump formula, small q square over g equals depth 1, depth 2 over 2, quantity depth 1 plus depth 2. So small q, 4.822 square over 9.81 equals depth 1, depth 2 divided by 2 times quantity depth 1 plus depth 2. Then, if you expand, that's quadratic formula. You can use your calculator if you want. Then, by high-tech calculator, we can now estimate depth 2 or compute depth 2 as 5.224 meters. Therefore, V sub 2 is small q 4.822 divided by 5.224. So this is the head loss formula. Quantity depth 2 minus depth 1 cube over 4 d1 d2. I already mentioned this. And if you want to see the derivation of this formula, you just look at the playlist on open channels in hydraulics rather than particular topic open channels. There is a question there about deriving the head loss in the jump formula if it is rectangular in section. So substitute quantity 5.224 minus 0.1683 cube over 4.1683 times 5.224. So head loss in the jump is 36.74 meters. Therefore, the energy at section 2 is 42 minus 36.74, and that is 5.26 meters. Likewise, let's solve for V2, and it is just small q is depth to V2. So small q divided by 5.224 equals V2, and V sub 2 is 0.923 square. The energy at section 2 or after the jump is velocity head at section 2 plus depth 2. So for quantity 0.923 square over 19.62 plus 5.224, and that is 5.267. So there's a small difference because of rounding of answers, but they are practically the same. So problem 2, the discharge over a Cepoletti weir is 0.52 cubic meter per second. The head on it is 1/4 of the length of the crest. What is the head in meters? So just remember the discharge formula for a Cepoletti weir, and that is equal to 1.859 length of crest head to the 3 halves. And since the head is 1/4 of the length of the crest, so the length of the crest in terms of the head, 4 times the head. So 0.52 equals 1.859 times length for h, then times h to the 3 halves. So solving for head, 0.52 divided by 1.859 divided by quantity 1.859 times 4, then the answer is raised to 2/5, which is the reciprocal of 5 halves because 1 plus 3 halves is 5 halves. So that's why the head is 0.345 meters. Problem 3, what is the ratio of the change in pressure to the relative change in density, and which also measures the compressibility of the substance? If you can recall, that's the bulk modulus of elasticity. Formula is delta P over quantity delta density over density, and that's the bulk modulus of elasticity. Also, the other formula is negative of delta P over relative change in volume. So That's why it's negative delta P over negative differential volume over volume. So that's also the other way. Problem 4, the three pipes are laid in parallel. The pipe characteristics are as follows. So we have pipes in parallel. And what is the flow rate in pipe A? This is pipe A. If the difference in heads at its ends is 40 meters. So the difference in heads at its ends is also the head loss of that pipe, which is equal to the head loss of the other pipes because they are laid in parallel. So for pipe A in particular, head loss equals 0.0826 FLQ square over diameter to the fifth by Darcy-Weisbach formula. So 40 equals 0.0826 times 0.02 times 600 QA square or Q square over diameter, which is 0.15 to the fifth. Solving for QA equals 0.05536 cubic meter per second. Then problem 5, extra problem now. What is the simplest device for measuring reverse stage? So it's like the Stadjarad, it looks like that, or a meter stick. We call that staff gauge. Then for B, the interface between immiscible fluids acts like an infinitely thin membrane that supports a tensile force. The magnitude of this tensile force per unit length of a line on this surface on this surface per unit length of a line on this surface, it's called surface tension, of course. So that's it for this video.